Okay, good afternoon everyone. So this is the 12th interactive session for NPTEL course Experimental Physics 1. The course instructor is Professor Amal Kumar Das from IIT Kharagpur and I am Rinalini, PMRF Research Scholar from School of Physics, University of Hyderabad. So this is the last interactive session for this course. And let's have a recap of what we discussed last week. So last week, that is interactive session 11, we discussed about the time constant in a RC circuit during charging and discharging method. We discussed its theory and then understood how the experiment works. After this, we understood the magnetic field along the axis of a circular coil and how we can use this concept to understand Helmholtz coil, which is usually used in our experimental labs to generate a uniform field, right? So this were things. One more thing was we understood the self-induced EMF due to an inductance coil. We discussed the Faraday's law of electromagnetic induction, the Lenz law, and also the experiment based on this. So we had understood that whenever there is a conductor placed in varying, that is changing magnetic field, an EMF is induced. So this was and we had understood what is self-inductance based on this. Now we'll see what is mutual inductance. So whenever there is a coil like this kind of coil, and we are passing current through it, there is inductance corresponding to it. Those conductance are of two types: self conductance or mutual conductance. Self inductance or mutual inductance. So inductance is effect caused by magnetic field of a current carrying conductor acting back on the conductor. So whenever we have an inductor and current is passing through it, then either because of the magnetic field passing through the, okay, let me draw it here. So if we have an conducting inductor coil like this and current is passing through it, then because of the current there will be magnetic field around this inductor coil, right? So because of the magnetic field there will be some action or some so there will be some acting back on this conductor, that will be self-inductance. But if we have two such inductor coil, and because of the current flowing in this inductive coil and the magnetic field as a result of it, if that affects something in another coil, then it's called mutual inductance. So we'll discuss those things. So again, recalling back Faraday's law of electromagnetic induction, which says that whenever a conductor is placed in a varying magnetic field, an EMF force is induced, and if the conductor circuit is closed, a current is induced, which is called induced current. This we had understood last time. To write it in the form of formula, the EMF, either we can use E or we can use V, anything is fine. So it is that it is proportional to rate of change of magnetic flux, due to that we are talking about it, varying magnetic field we are talking about. So when magnetic field is changing, magnetic flux is magnetic field corresponding to perpendicular area. So this is flux, and when that magnetic field or that flux related to that particular area changes, we get EMF in the circuit. So this is what this law says. Now if we talk about then Lenz law also, was, as we had discussed, it tells about the direction of the EMF induced, which says that it opposes the origin, it opposes the cause that is making it to get the EMF. Anyway, so yeah. Thing is, if we have, let me write here. If we have, as I said here, if we have one coil, then the EMF induced in this coil, let me again draw here. If we have this coil, and say the length of this coil is some L and current I is flowing in this, then the EMF induced in this will be inductance times di by dt. This we had discussed last time. And the inductance is given by mu naught n square, where n is number of turns in this coil, times A is the area of cross section, divided by the length. Okay. The length of this coil is small l. So this is related to the single inductor. If we have two coils, this is coil 1, this is coil 2, then there will be inductance here due to coil 1 on coil 2, that is called mutual inductance, di by dt. And the mutual inductance, the formula for mutual inductance is M, which is mu naught, which is permeability, and number of turns in coil 1 and number of turns in coil 2, times A2 divided by L1. So here we need to keep in mind that area is corresponding to the second coil and length of the coil is due to the first coil in which we are flowing the current. So current we are flowing in coil 1, and due to this flowing current there is a magnetic field around it. Because of that magnetic field there is EMF getting generated in the second coil. That we are saying mutual inductance is there, and the formula consists of the number of turns in coil 1 N1, number of turns in coil 2 which is N2, and area is of the coil 2, and length of the inductance coil depends on the coil 1. So this is the formula. Now let's find out the working formula. So for working formula, what will be the induced EMF in secondary coils? So from the Lenz's law or from the Faraday's law, as we know, EMF is, if we ignore the magnitude, if we just focus, if we ignore the sign and just focus on the magnitude, then we know EMF induced is the rate of change of magnetic flux. What is that flux? It is product of magnetic field and the magnetic field due to. So let's call the coil 1 and 2, instead of calling them 1 and 2, let's call them primary coil in which we are flowing the current. Let's call it primary coil, and the other one, let's call it secondary coil. So magnetic field, because we are flowing current in primary coil, so the magnetic field is also corresponding to this primary coil. This is BP, and the area is corresponding to the secondary coil, right? So area of secondary coil and number of turns of secondary coil. So this is the magnetic flux. Since by definition we know that the EMF generated in this second coil, that is the secondary coil, as we saw here, this is by definition we are using the mutual inductance for these coils. Is someone saying? Okay. What is just okay. So the EMF induced in the secondary coil will be this mutual inductance constant and the rate of change of the current flowing in the primary coil. If the current that is flowing, it is an AC current, then we can write it in sinusoidal form, right? In that case, how this will become? It will be, this is a constant, and when we'll substitute this primary current value here, we'll get omega I naught cos omega t. So yeah, so from this thing, when we'll substitute here, we'll get the EMF corresponding to secondary coil, or we can write it like this also. When we'll substitute these values here, again this from this formula, just a second. So by definition, Vs was this, but from this rule, actually, okay, this is one expression. From this law, the EMF will be, since BP, which is generated due to primary coil, it will be mu naught NP IP divided by LP. When we'll substitute this here, we'll get, I'm taking derivative, the final thing we'll get is mu naught NP NS AS divided by LP. There will be cos phi and dIP by dt, which again, when you do the substitution, let me write this here. Okay. So this cos phi that is there from dot this P dot AS is there, right? That's why from this dot product this cos phi is coming. It is the angle between the direction of magnetic field and the area vector. We know that. Okay. So the value of MSP, when we'll compare this and put it here, this expression that we have derived, and the Vs here, when we compare this, we'll get the value of MSP, mutual inductance value, which will be mu naught NP MS AS divided by LP and cos phi. So this is our working formula, right? So this is our working formula, and in CRO that we use when we measure this induced EMF, we measure this Vmax actually there, and Vmax is peak to peak value. So in CRO we get values like sinusoidal wave values you will get, right? So when we are calling peak to peak means this maximum to maximum, minimum, or you can say maximum on the negative side. So this value we are calling V peak to peak. This is the value. So maximum is V peak to peak, half of it, which will get MSP I naught omega over 2. Okay. So yeah, now in the experiment, for experiment again, it's best to refer the videos, because we'll move on to the next experiment now, which was determining permeability of air. So what is permeability? It is the ability of any material to allow magnetic field lines to pass through it. How easily any material lets magnetic field to pass through it. This is known as permeability of that material. So the experiment it was to measure the find out the permeability of air. The experiment that was discussed was to find out permeability of air. this was the experiment. So just let's understand the working, how to get the working formula for this experiment. So to find out this experiment, we are considering two rods, two conducting rods. Okay, they are put parallel. Recalling our knowledge about what happens when current passes through a conductor, we know magnetic field is generated. If we are passing current in this conductor, there will be magnetic field. From right hand thumb rule, you know, there will be magnetic field around this conducting rod. When we have two such similar rods kept together at some distance, say d naught, then if the current is flowing in the same direction, if the current is flowing in the same direction, then they will attract each other, the magnetic field. When they will be opposite direction, they will repel each other. So in this experiment, we are considering that there is I1 and I2 current flowing in these two rods, and there is air between them, and we want to find out permeability of this air medium. Now since we know Lorentz force between two long wires is given by the formula mu over 4 pi 2 I1 I2 times L, which is the length of these conductors, divided by the distance between them. If the current is same, then it will become I square, and if we cancel this 2 and 4 also, finally we will get mu over 2 pi I square L over D, and from here we'll find out the permeability value as 2 pi d0. Actually, we can define something else. If the rods are of some significant thickness, then there will be their radius also, right? In that case, if you want to consider correct value of distance, then we should consider their radius also. In that case, we can write something like d1 is d0 plus r1 plus r2. Then we can define even better, correct, with more accuracy, and we can call it d1, right? 2 pi d1 over L and f over I square. This is the working formula for this experiment. This is I square. This thing is a constant, so in this experiment we need to measure the force and measure the current, and when we will plot force versus I square, we will get a linear. From the slope we can find out mu. So this is the working formula for this experiment, and you can understand the experiment from the lectures. And here again we will further focus on doing this previous year assignment problem. So let's do those. So first question is, a wire has a resistance 16 ohm. There is a wire which has a resistance of 16 ohms. Now it is bent in the form of a circle. Okay, the effective resistance between 2 points on any diameter of the circle, it's drawn already here. And just, if we take diameter of this circle, then the resistance between any 2 points, so the wire is here, right? And we have to find out the resistance between any 2 points. Means, let me redraw this. This means this A point and B point is there, and this is there, and then this is there. So this wire that I put it in form of circle, right? Its resistance was 16 ohm. That means half wire resistance will be 8 ohm, since we know resistance is directly proportional to length, right? So if I consider half wire, that means its resistance will be 8 ohm. That means this one part has 8 ohm resistance, and this another half part has 8 ohm resistance. Now we need to find out resistance between point A and point B. So we can clearly see here these two resistors are in parallel, right? This the way we have been asked to find out the resistance, that is like we have to find out the resistance, overall resistance for these two parallel resistors. So we know what is the formula to find out the total resistance for parallel resistors. That is, the resistance will be 8, right? It's R1 R2 divided by R1 plus R2, and that will be 16. So the final answer will be, this will be what, 4 4 ohms. So the equivalent resistance between any two point in this circle will be 4 ohm. So C is the correct answer here. Now question number 2. We just, the recording is going correct. Yeah. Okay. So same question is, a wire of resistance 3 ohm is stretched to twice its original length. So there is a wire of resistance. There is a wire of resistance 3 ohm, and after this is the original length. So let's call the original length, let's say it's L. Then it's stretched and it becomes twice its original length. So it changes, sorry. So it changes and we stretch it to make it twice, and volume remains unchanged. So if the volume earlier was V0, now also the volume is V0, but the length has increased, means the radius would have decreased, right? Because the volume has to be constant. And now we need to calculate the new resistance for this. What is the new resistance here? We know resistance is directly proportional to length and inversely proportional to area, means, and we know area is pi r square. So we need to find out what is the radius, how the radius has changed. So earlier, let's call, if the radius was r0, then what is this r1? One thing we know is volume is same, okay? uh, Volume is same, and volume of wire is like a cylinder, as we had discussed earlier several times. So volume of a cylinder is pi r square h. For this, radius is r naught, so pi r naught square, and that h is actually length of this cylindrical wire here, so that is L. This volume is same as after stretching, so this will be pi. New radius we don't know yet, and the height of the cylinder means the length of the wire, which is 2L. Now we'll find out the value of R1 out of this. So this pi will cancel, L will cancel, so R0 square pi 2 is R1 square. This means this new radius is R0 divided by root 2. This is the new radius. Now the new resistance will be new, okay. So old resistance, okay, let me see. So old resistance, which value was 3 ohm, it will be some resistivity of the wire will not change even after stretching, right? It's the property of the material. So resistivity times the length was L and the area, let me write pi r naught square, and this was 3 ohm. Now the new one will be resistivity, length is 2 times L and area is pi r1 square, and r1 square is what? R naught square divided by 2. If I rewrite this, it will become 2L divided by pi. Well, R naught square means 2 R naught square. As you can, if you compare this 1 and 2, don't confuse here. This is 2 and this is actually square. If we compare these two, we'll see this rho L over pi r naught square. Rho L and pi r naught square is the resistance of the old wire. And apart from that, we are getting 2 times 2, that is 4. Right? Now what was the resistance earlier? It was 3. 3 times 4 means 12 ohm. That means old wire had resistance of 3 ohm. Now the resistance has increased 4 times and has become 12 ohms. And the correct answer is 12 ohms. Okay. Next question. A straight horizontal conducting wire. Straight horizontal conducting wire. Let me draw here. There is a conducting rod of length 0.5 meters and its mass is 0.1 kg. It's suspended by 2 vertical wires. So this itself is a rod, cylindrical rod, and it's suspended by 2 vertical wires. Okay. A current of 10 ampere flows through the rod. Current of 10 ampere is flowing through the rod. The magnetic field required to be set up normal to the wire. Okay, normal means perpendicular to the wire, so that the tension in the wire is 0. Means we know, because of weight of this rod which is suspended with 2 ends on these wires, because of this there is tension in the wires. If we support this weight of the rod from opposite direction, then the tension in the wire will become 0. So how much is the magnetic field required to be set up normal to the wire so that the tension in the wire is 0? So tension of wire is due to weight of rod. So the tension is due to the weight of the rod. Now we know that because of the current flowing in the rod, there will be magnetic field. What will be the value of that magnetic field? I mean the force of force due to this magnetic field. The force will be I L cross B. That means this is cross product, means sine theta, and what is the direction between this? Theta will be 90 degree, right? The current is flowing in this direction and we want to find out the force in this direction. I mean the length is in this direction and magnetic field is in perpendicular direction. So sine 90 degree it is, and we know sine 90 degree is 1. So this will be I L B. Now force and this. Now this force has to be equal to the tension force. So when we equate them, this mg and this ILB, we need to find out how much magnetic field is required. So B will be mg over IL. Now when we will substitute the values, mass is 0.1 kg, value of gravity we have been asked to take 10 meter per second square divided by the current is 10 ampere and the length is 0.5. Now let's this will be cancelled, so this will be let's just calculate 0.1 divided by 0.5, that will be 0.2 Tesla. So the correct answer is 0.2 Tesla. Okay. Now the next question. A circular coil of wire of 50 number of turns and area is given to be 0.05 meters square. So a circular coil of wire where number of turns is 50 and area of coil is 0.05 meters square and the current flowing in this coil is 1 ampere. Okay, current is 1 ampere. The wire is suspended vertically in a uniform magnetic field of strength 1.5 Tesla. So there is field here and that field value is 1.5 Tesla. Determine the maximum magnitude of torque may act on the coil. So the torque that will act on this coil, the value we know, the formula, it's IB. These are all vectors, but we are just interested in the magnitude. So IB NA. And since we have been asked to find out the maximum magnitude of torque, the maximum will be IB NA, which will be 1 and magnetic field is 1.5. Then number of turns is 50 and area is 0.05. When we calculate this, we will get 1 times 1.5 times 50 times 0.05 is 3.75. So the torque value will be 3.75 Newton meter. This will be the maximum torque for this circular coil of wire, 50 number of turns, where which is suspended in magnetic field value of 1.5 Tesla. So the maximum torque acting on it will be this. And yeah, the value is this. This is the next question is, a solenoid has mean diameter of 0.05 meter. So there is a solenoid. Its diameter is given 0.05 meter. Its length is 2 meters. There are 4 layers of this of 1000 turns each. Since there are 4 layers of 1000 turns each, means we can consider it like 4 times 1000 number of turns anyway. And a current of 2.5 ampere flows through it. And the current flowing is how much? 2.5 ampere flows through it. The magnetic field at a point on the axis S1. So this we had done like previous week, that magnetic field due to this kind of current carrying solenoid at one end of the coil, magnetic field will be mu naught, number of turns per unit length, and Ni over 2. Right, the small n is number of turns per unit length. So the value will be mu naught. The value of mu naught is 4 pi times 10 to the power minus 7. Number of turns is 4000, and this is actually number of turns per unit length. There are 4 layers and 1000 turns each per unit length. Length is 2 meter. Okay, so this we'll put here. So it's 2000 number of turns per unit length, and current is 2.5 ampere divided by 2. So the value we'll get is, it will be actually 2.5 times 4 is 10, and 10 to the power 4 times pi times 10 to the power minus 7. It should be 4 minus 7 is minus 3. It's 3 pi. If you put the value of pi, then it will be 3.14 times 10 to the power minus 3 Tesla, or we can call this millitesla. Okay, so here the answer will be 3.14 times 10 to the power minus 3 Tesla. This is the correct answer. Now the next question. A very long straight conductor carries a current of 25 ampere. We have a very long straight conductor carrying a current of 25 ampere. An electron is traveling with the speed of, okay, so electron is traveling with the speed of 8 times 10 to the power 6 meters per second. Parallel to the wire, it's moving, okay, so it's also moving in this direction at a distance. The electron is at a distance of 0.01 meters. This is 0.01 meters from this current carrying conductor. The electron will experience a force. So since there is current flowing in this conductor, there will be magnetic field, and because of that magnetic field, there will be force on this charge, moving charge. And what is that formula? So first we know when there is magnetic field, and in that magnetic field a charged particle is moving, then it experiences a force which is given by this formula, right? QV cross B. This is charge, so charge here a negative electron. Before that, we need to find out what is the value of magnetic field due to this current carrying conductor. So the value of magnetic field, just let's see the magnitude. So value of magnetic field due to this current carrying conductor will be mu naught over 4 pi times 2 times the current divided by the distance. So here mu naught is 4 pi times 10 to the power minus 7, right? You know the value of mu naught is 4 pi. Permeability of air, this is 10 to the power minus 7. So when we'll substitute, 4 pi will cancel and we'll left with 10 to the power minus 7. 2 times the value of current, which is 25 ampere, divided by the distance, which is 0.01. When we'll solve this, we'll get, this will be 50 and 10 to the power minus 7, and this is 10 to the power minus 2. It will come and become plus 2. This will be 50 times 10 to the power minus 5 Tesla. This is this. Now when I substitute the value of magnetic field here, there is the charge of electron, actually we take 1.6 times 10 to the power minus 19 coulomb. So using the same thing here, 6 times 10 to the power minus 19, and velocity we have been given 8 times 10 to the power 6 meters per second. Everything is in SI unit, and magnetic field value we found out 50 times 10 to the power minus 5 Tesla. Now let's calculate everything. So it will become, let me calculate, this will be 1.6 times 8 times 50, that is 640, and these powers, that will be minus 19, 6 minus 19 minus 5, that is minus 18, 10 to the power minus 18, the force SI unit will be Newton. Now okay, so we see something, magnitude is matching here, just changing the powers. So I can write it like 64, right? 10 to the power minus 17 Newton. So the correct answer is this. This we've calculated till here. We just need to take care of the number of we can we can move the decimal point up to here also, here also, here also. So whatever the answer option was available, accordingly we adjusted the answers. So the correct answer here is A. Okay. So the next question is about magnetic field at a point P. Magnetic field at a point P, which is at a distance of 4 centimeter from a long current carrying conductor. So we have a long current carrying conductor. And from 4 centimeter distance at point P, we need to find out the magnetic field. And due to this long current carrying conductor, there is field of 3 times 10 to the power minus 3 Tesla. This is the field due to this current carrying conductor. We know the formula for magnetic field due to current carrying conductor is mu naught over 2 pi I over R. Since we have been given that the magnetic field value is 3 millitesla, and we will substitute the values here to find out what is the value of current, because we have not been told what is the value of current flowing in this, right? We have just been told the magnetic field due to this current flowing in this conductor. So we will find out from here. So value of mu naught is 4 pi 10 to the power minus 7 divided by 2 pi times the current we need to find out, and the distance between the point and this current carrying conductor is 4 centimeter. I'll change it to SI unit, that is 4 meter. So 4 centimeter and SI unit will be 0.04 meters, right? 0.04 meters, and we'll equate it to 3 millitesla. From this, when we'll solve this, 2. Okay, so I will become 3 times 10 to the power minus 3 multiplied by 0.04 divided by 2. So when we'll calculate this, we'll get the value of I. Let me calculate this. Plus 0.04 divided by 2. 0.02 times 3, 0.06. 0.06 times 10 to the power minus 3 ampere. This is the current value that we have obtained from here. Just so this is the value of the current. So we get to know this is the current flowing in this. Now we need to find out the magnetic field at point P. So we know the distance will change, and the magnetic field at point P will be mu naught. The same formula we'll use, only the value of R will change. Now we know the value of I, so we will substitute that. It will be 2 pi. And the value of I is 0.06 times 10 to the power minus 3, and the value of R is 4 centimeter. Right. Wait, sorry, this point P, okay, I'm sorry, the point P was at distance 4 centimeter. We calculate the current using this. Now we need to find out magnetic field at distance of 12 centimeter. This is not at point P, sorry. This is at some distance 12 centimeter away. It is, let's call it point Z. Okay, so the magnetic field at point Z here will be 12 centimeter, means 0.12 meters. When we'll calculate this will be again mu naught, the value is 4 pi 10 to the power minus 7 divided by 2 pi, so it will be, this will be 0.6 divided by 0.12 is 5, okay, 5 times 10 to the power minus 3, 5 over 20, it will be 20 times 10 to the power minus 7, oh there is 2 also, so this is 10 times 10 to the power minus 7, sorry I don't have space here, so this magnetic field at Z point will be 10 times 10 to the power minus 7 Tesla. So you can write it like, no wait, what happened? It's some mistake. 4 pi into 10 to the power minus 7, 0.6 into 10 to the power minus 3. I think everything is fine. And then we do some mistake over 3 millitesla. I think this current value is correct. 3 times 0.04. 0.12 divided by 2 is 0.06 10 to the power minus 3. That is correct. 10 to the power minus 7. 10 times 10 to the power minus 7 means it's a mistake. I'm sorry, we are okay. Think mistake. Did we? Models? Okay, I'm sorry. Shall we do it again? Because I'm not able to find out where is the mistake. This is 10 to the power. Oh, the answer is in. Maybe it's none of those. Okay, let's first do other questions, then we'll come back to this one. There is something wrong happening here. Okay, so the next question is about two identical coils. These are the coils which are perpendicular to each other. We can see they are carrying equal current, means they are carrying same current and have common center here, but the planes of the coils are at right angles to each other. You can see the plane of these coils are perpendicular to each other. What is the magnitude of the resultant magnetic field at the center? So we know because of like if we have a coil, then because of this such a current carrying coil, the magnetic field will be in this direction, right? And if we have a coil like this, the magnetic field because of this along the axial, or if I take it here along the axis, will be in this direction. That means the resultant because of this coil, let's call it coil 1, the magnetic field will be in this direction, and because of the other one it will be in this direction, right? It will be in both this side and this side, but here if you see it will be this. So okay, this is coil 2, because of it the magnetic field is here, because of coil 1 magnetic field is here. So let's find out those two values, and then resultant will be actually this. The resultant of these two will be in this direction. So first let's find out what is the value of B1, B2. Oh, actually we have not been given any magnitude, so we cannot calculate. We just need to tell this final one. So since it's vector addition, we know from vector addition that we can move this here, right? We know b1, we know b2. We need to find out this resultant value b. Let's call it br. So br will be b1 squared plus b2 squared. And since these magnitude of magnetic field due to these two coils, magnitude will be same because their radius is same and the current they are carrying is same. So their b1 and b2 are same. Their magnitude is same. So it will be 2b square. So that means br will be root 2b. So the correct answer is root 2b. This is the correct answer. Okay. So there is another question here. Okay. I think there is, okay. This question is that there is an alpha particle and a beta particle. Alpha particle we all know, it's actually like a helium particle, so helium atom, if you know, it's a 2 atomic mass unit, right? So that means it has 2 protons and 2 electrons, right? Its atomic number is 2. That means it has 2 electrons and 2 protons. 2 electrons and 2 protons helium has. But when we say alpha particle, so that is actually a helium atom in which we have removed these 2 electrons. Alpha particle, a helium atom becomes alpha particle when these 2 electrons have been removed, and then the charge on it will be only because of, so helium atom is neutral because it has same number of electrons and protons, but when we remove these 2 electrons, the charge on the alpha particle will be because of these 2 protons. So it has 2 proton charge, or the magnitude of charge is same as electron, but the charge is positive. So this is the charge on alpha particle. So we have an alpha particle and we have a beta particle. Beta particle is plus negative electron charge are moving with equal velocities. Okay, so alpha particle is also moving, and beta particle, that is this electron, is also moving with same velocity and perpendicular to the direction of uniform magnetic field. So there is some uniform magnetic field and both of them are moving perpendicular to that direction of field. If the magnitude of forces on alpha and beta, so we know that if there is magnetic field and charge is moving in that magnetic field, then there will be force acting on it, and we know that value of force is given by this, which depends on the velocity of the charged particle and its charge and the direction of the velocity with respect to the magnetic field. Here the magnetic field and velocities are in 90 degree to each other. Cross product means b sine theta. Now that theta is 90 degree and sine 90 degree is 1. So the force due to on these charges will be QVB. Now we need to just, their magnetic field is same for both, their velocities are also same as given. Now only the charge on them is different. So we have been told that the force on alpha particle, if we call it F1, and the force on beta particle, let's call it F2, then what, due to the field acting, so what is the relation between these two forces? So F1, which is alpha particle, the force on it, because the charge is, as we told, 2 times the electron charge, so Q will be this, and B is same, B is same. For beta particle, that is F2, the charge on electron represented by small e velocity is same, magnetic field is same. So we can clearly see that F1 is 2 times F2. So the relation between F1 and F2 is F1 is double of F2. Okay, this is the relation. F1 is 2 times F2. This is the correct answer. Okay, so next question is semicircular wires of radii R1 and R2, as can be seen from this diagram. They are semicircular wires of radii R1, which is smaller, as we can see R1 is smaller than R2. They carry the same current I, only the direction of current is changing. Here the direction is like this, and in this R1 circle the direction is opposite. What is the magnetic field at the center? C. Okay. So magnetic field due to semicircle, what will be its formula? So magnetic field due to semicircle, we know, is given by mu naught over 4 pi. So for whole circle it's 2 pi I. So for the semicircle it will be divided by 2, and then the radius. So the resultant formula is mu naught I over 4 R. This is the resultant formula. So the magnetic field due to R1 radius, its value will be mu naught over magnitude, we are talking about I over R1. So the R1 is actually capital R1. I should write this also capital. And the magnetic field due to R2 will be mu naught over 4 I over R2. Since R1 is smaller than R2 and current is in opposite direction, that means the resultant force, the currents are flowing in different direction, means the magnetic field will be because of one semicircle it will be in one direction, and because of this remaining semicircle it will be in opposite direction. So the resultant magnetic field at the center will be subtraction of this, and since R1 is smaller than R2, so that means since R1 is smaller, that means this field is large value than BR2. So we'll do BR1 minus BR2. We'll get mu naught over 4 I also will be common, 1 over R1 minus 1 over R2, right? Since we clearly see R1 is smaller than R2, so and R1, R2 are in denominator, so we can say BR1 is magnetic field due to R1 is more than magnetic field due to R2, and from that the resultant magnetic field at the center will be the subtraction. So the correct answer is mu naught or mu. Permeability they have taken as mu. We have taken mu naught, that's fine. Mu naught I by 4 and 1 over R1 minus 1 over R2. I think the option A is the correct option here. Well, A is the correct answer. Let me just... Okay, what happened? Okay, so that was those questions. Now let's do this question in which we had got doubt regarding something. Let's try this again. So first, what it's telling is the magnetic field at point P. Again, there is point P, and it is at distance 4 centimeter from a long current carrying conductor, and the magnetic field at point P, magnetic field value we have been given at point P, which is 3 times 10 to the power minus 3 Tesla. This is the value. Now so So the magnetic field, we finally need to find out at distance 12 centimeter from the same wire. So magnetic field we are given. To find out magnetic field at 12 centimeter, we need to know what is the current flowing in this wire. That we have not been told. So from this information, we will find out the value of current first. Since we know that magnetic field at any point from given current carrying wire is given by the formula mu naught over 2 pi times the current divided by the distance. This is the formula. Here, if we say about at point P, then the value is 3 millitesla, that is 3 times 10 to the power minus 3 Tesla. Now substituting the value of mu naught, which is 4 pi times 10 to the power minus 7. Okay, so mu naught, yeah, or should I, even if I, okay, let me just find out what will be the value of current from here. The current will be 3 times 10 to the power minus 3 times 2 pi times r divided by mu naught. This will be the current. Now the magnetic field at point 12 centimeter away from the current carrying wire, it will be mu naught over 2 pi. The value of current I'll substitute. The distance is 12 centimeter, which is 0.12 meters. So this will be mu naught over 2 pi. The value of current is 3 times 10 to the power minus 3 times 2 pi. And what was R there? R was 4 centimeter, that is 0.04 divided by mu naught and 0.12. Right? From here mu naught cancelled, 2 pi cancelled. Now let's calculate the remaining things. Let me use the calculator this time. From calculator, 3 times 0.04, okay, divided by 0.12 is 1, and it will be 10 to the power minus 3. That means the answer is 1 millitesla. Okay, so the answer is this. I don't know earlier what was the mistake, but if we are doing it like this, we are getting the correct answer. So yeah, 1 millitesla is the correct answer. So that's all the questions. About the mutual inductance this time, right? And based on this, we did previous year questions. So this was the last session. Okay. Thank you for joining and asking questions, and I had a great time teaching you guys. Okay, thank you. So I'm ending today's session. Thank you.